All right, we're looking at limit methods in polynomial and rational functions. So if you've done the preamble, then you've been faced with things like this. The limit as x approaches 1 of x squared plus 2x minus 3 over x squared minus 1. And when we put 1 into this expression, we get this 0 over 0 if we just go ahead and substitute 1. But that's the value of the function at 1. That's not really the limit at 1. So we can fix this whole 0 over 0 issue. And so what we are going to do is we're going to factor the top and bottom and see what happens. Maybe we can fix this. So the top comes to x minus 1 over x plus 3. And the bottom I recognize as the difference of squares, so that's x minus 1 over x plus 1. There we go. We factored it. Now, here's this thing that's causing this 0 over 0 condition. It's this. Okay? So I can cross those out, and suddenly I have an equivalent expression here, x plus 3 over x plus 1. And I can actually plug in my limit safely now and come up with an answer. Oh, sorry, everybody. I left my limits off here. Please don't do this. I'm supposed to give you a big red X if you do this on your test. And when I plug this in, the 1, I can just do that. It's 4 over 2 R2. So in fact, the limit as x approaches 1 of this expression is just 2. If you looked at this in, if you were to look at this in Desmos, you would actually see something that looks like an ordinary sort of rational function. It'll have a vertical asymptote when x equals -1. But it won't have a vertical asymptote when x is equal to +1. And you might wonder why. And the reason why is these two parts cancel out. So I encourage you to take a look at it. You'll see that as x approaches 1, you'll see the graph approach 2. And if Desmos does its job, when you're sliding along that little graph, you'll actually see that it says undefined as soon as you get to 1. So once again, the limit exists. The function does not exist right there. Miracle? I think so. Okay. All right, let's look at this because this is a little bit interesting. Okay, so question is, does this limit exist? And if you've done the preamble, you'll see that actually this limit does not exist. It's kind of scary. Why don't we simplify this just a little bit? I'm going to take the x off there because I don't think it matters so much for this example. So the question is, what is the limit as x approaches 2? And this is the absolute value of x minus 2 over just regular x minus 2. Now, the absolute value function can be better explained as a piecewise function. So the absolute value of x minus 2 is the same as just x minus 2 when x is greater than +2. In other words, when x minus 2 is positive, it's just x minus 2. And it is negative x minus 2 when x is less than 2. And so we can redefine the absolute value function as this piecewise function. And we can now break this up into two cases. We can look at this as being the limit as x approaches 2. And if we're going to approach it from above, in other words, when x is greater than 2, well, then we're just looking at x minus 2 over x minus 2. Pretty simple. if we're approaching it from below, well, then we're looking at it being negative x minus 2 over x minus 2. So this is case 1, and this is case 2. Okay, so this is easy. Oh, look at that. This can cancel down to being just 1. So the limit as x approaches 2 from above is 1. Now, what does this one become? So this is case 2. We have to flip the sign on our top expression because we're approaching 2 from below. Here comes case 2. These cancel out. The top becomes negative 1. The bottom is positive 1. And so the limit as x approaches 2 from below is negative 1. So look what just happened, everybody. When we approach 2 from above, it's positive 1. When we approach 2 from below, it's negative 1. The left and right limits aren't equal to each other. And so this limit does not exist. Okay, so there we go. Does not exist. So once again, it's a matter of breaking it up into these two cases, recognizing that you can write an absolute value function in this piecewise format, and then noticing that there's a jump discontinuity right at the location of this limit. So that's the absolute value function. It's maybe the most it's the most complicated one in this lesson, and we actually are not supposed to spend that much time on it in high school, but they do tend to spend a bit of time on absolute value when you get to university. Okay, let's look at this. Limit as x approaches 3 of 1 over x minus 3. And so this is just a simple reciprocal function. And if we look at this, we learned how to graph these in advanced functions pretty easily. So if I plug in a 0 into this, I get a 1 over 0, that's bad news. I have a vertical asymptote when x is equal to 3, so there's my vertical asymptotes. Let's see, this thing tends to 0 as I go to negative infinity, and it's negative right up till here. So there's the first part of it. And when x is greater than 3 and really, really small, so, or sorry, just a little bit greater than 3, so like 3.00000001, it's really big and infinite. And as x gets really big, this expression tends to 0. Okay, so I'm asked to find out what the limit is as x approaches 3. Well, I can certainly see that they are not equal in any way. This is an infinite discontinuity. The left limit and the right limit aren't equal. Not only that, the function doesn't exist there. And so that limit does not exist, DNE. All right, let's fix this. Let's make this squared on the bottom. Okay, so same, we're going to approach 3. We have an x minus 3 squared on the bottom instead of an x minus 3. And this looks a lot the same, except you'll notice, of course, this would be a little bit steeper. But the bottom is always positive. This expression is always positive. As x gets really, really close to 3, like 2.99999, this is going to become a really big value. And then when x is just a little bit greater than 3, like 3.000001, it's going to be a really big value. So as we approach 3 from below, this thing heads for positive infinity. As we approach 3 from above, this thing heads for positive infinity. But infinity is not a number. It is an idea more than anything else. And so we just say, well, that limit does not exist. Even though we tend to talk towards, it does say that it tends towards.
Sometimes they put it as the limit here would approach.
The limiting value would head for infinity, yeah. That's the way it gets expressed. And it's often expressed as the value of the function in the limit approaches infinity. Really, the limit doesn't exist because infinity is not a number. Okay. So here we go. Summary. When we're dealing with polynomial and rational functions, factor them. Look to cancel out those values, especially when you're in that 0 over 0 phase, okay? So just be careful because even though you get 0 over 0 if you do the substitution, maybe that limit really does exist because approaching from the left and right, it goes towards a number. When you're dealing with the absolute value function, consider the two cases as it approaches the limit from above and the limit from below, because those ones can generate these little jump discontinuities. And then when you're dealing with rational functions and you're in that situation where you're approaching the value that makes the denominator or the bottom of that rational function 0, then probably the limit doesn't exist. And it's that simple. Okay, I think it's actually pretty straightforward, so factor a lot. That's it.